In this video, I want to take a look at an example of a vector space that uses objects that we're very used to, but thinking of them in a different way as to how we combine them together. So here's what I want to do. I want to look at the set V, which is all positive real numbers. So not negatives, not zero, just positive real numbers. These are going to be my vectors, right? And I'm going to distinguish between the vector, I use a little vector symbol, or the number itself. So when I say the vector 3, I'm talking about the number 3. Okay. So what I need to do is I need to define addition and scalar multiplication. So addition I define this way. To add two vectors together, I'm going to multiply the real numbers together. For instance, the vector 3 plus the vector 4 is 3 times 4, which is 12. So that's the vector 12. So the vector 3 plus the vector 4 is the vector 12. Okay. Likewise, if I take a real number and multiply it by the vector, I'm going to take the real number u and raise it to the k. So essentially 2 times the vector 3 is going to be 3 squared, which is the vector 9. So 2 times the vector 3 is the vector 9. So I've got my two operations defined here. The question is, do these two operations satisfy the 10 axioms of a vector space definition? So let's check. Is addition closed? If I take two vectors, which are two positive real numbers, and I multiply them together, right? That's what I mean by adding. If I add the vectors by multiplying the numbers, does that give me a positive real? Well, sure. Product of two positive real numbers is a positive real number. So yes, addition is closed. I'll check that off. Is addition commutative? So if I take u plus v, by definition, that's u times v. But I know that real number multiplication is commutative, so that's v times u. But that's what you would get if you added the vector v to the vector u. Right? So yes, addition is commutative. That is, addition of these vectors is commutative because multiplication of real numbers is commutative. Is it associative? If I take u plus v plus w, three vectors here, group it like this, can I change the grouping? Well, this would mean the vector u plus the vector corresponding to the product of u and w, sorry, v and w, which would be u times the v times w, which, this is now all just scalar multiplication. This is real number multiplication. So this is u times v times w, because that is, in fact, the way you multiply. I mean, multiplying real numbers is associative. Inside the parentheses, no, outside the parentheses, this would be the same as the vector uv added to the vector w. But the vector uv is what you would get by adding u and v, right? That if you multiply the two numbers together and then take that as a vector. So this is equal to that, sure enough. Okay. Is there a zero vector? Is there an additive identity? So given any number, so given a vector u, is there something you can add to it that's going to end up with u again? And the thing is, if you take 1 as a vector, right, this would equal u times 1, which is just u. So 1 is the 0 in this vector space. 1 is the additive identity, because by adding, put that in quotes, adding, I'm actually multiplying. Are there additive inverses? Well, maybe if 1 is the additive identity, the additive inverses might be reciprocals. So if you take u plus the vector, which would be 1 over u, this would mean u times 1 over u, which is 1, which is the 0. And I'll denote the 0 vector this way. Well, actually, the number 0 is not in my set, is it? But, well, yeah, this is tricky. 1 is my additive identity. It's my 0 vector. Right? And so these added together to be the 0 vector, so they're additive identities. Right? Is scalar multiplication closed? If you take any real number k and multiply it by the vector u, which you're getting u to the k, is that still a positive real number? Yes. Okay, so that's good. Do we have a distributive property here? Right? If I take a scalar times the sum of two vectors, well, that would be the real number k times uv, but that would be, well, sorry, the vector corresponding to u times v, which would be u times v, oops, raised to the k power. But there's a property of exponents that if you raise this product to the k power, that's the same as u to the k times v to the k. But this is what you would get if you added the vector u to the k plus v to the k, but the vector u to the k came from k times u, and this thing came from k times v. So is there a distributive property? Yes, there's a distributive property. And really what it is essentially saying that this property of exponents distributing over real number multiplication is a distributive property. It's just like multiplication distributing over addition, just that you're in a different vector space. Likewise here, if I've got k plus m times the vector u, well, by definition, that's u to the k plus m, but we know how real numbers work. That's u to the k times u to the m. But this is two numbers being multiplied together now, which is u to the k as a vector plus u to the m as a vector, which is equal to ku plus mu. And so the distributive property works that way as well. That's another property of exponents where it's like a distributive property, and it is a distributive property in a different vector space. How about this one? If I have k mu, this would be k times the vector corresponding to u to the m, which would be u to the m to the k. And how do you do a power number to a power to a power? Well, you multiply the two things together. This would be u to the km, but that's km times the vector u. Okay. And lastly, if I have u times 1, by definition, that would be the number u raised to the 1 power, but that's just equal to u, which is the vector u. So this is a vector space. We've essentially defined addition as multiplication, and we've defined multiplication as exponentiation, right? Raising it to a power. Notice I had to take positive reals. If I took 0 in there, I'd have trouble finding an additive identity, because 0 times what equals 1? Right? sorry, additive inverses would be a problem because 0 times nothing. There isn't anything you multiply by 0 to give you 1. So 0 doesn't have an additive inverse. But since 0 is not in this set, I don't have to worry about it. Okay. So anyway, this is a vector space with addition defined this way and scalar multiplication defined that way.